Oh, I gotta shut my door. Thank you. Ow. All right. Hi, class. Okay. Last time we were talking about specific heat capacity. Q is the heat, and C is the specific heat capacity. So I thought I'd start there. How do you define heat? Transfer of energy, very good. It's energy in transit. Does an object possess heat? No. Does an object contain work? No. An object can do work, and an object can transfer its internal energy, and that's what we call heat. Good. I think if, in thinking about all this stuff, if you remember that, that'll help you out a lot. Won't fall into a lot of traps that I did. Okay. So, what determines? We've been discussing this formula, and then I laid it on you last time. What matters if heat is going to transfer? I'll throw that on there, transfer. What's that's dependent upon, proportional to, is how much of the thing you have. And you know that, which I tried to discuss it, if you have a big pot of water and a small pot of water, and you apply the same heat to it, which one will heat up faster? The small, because you got less of it. If you got more, you're going to need to transfer more heat into it to have the same effect, trying to raise its temperature. It also matters what the material is. What it is. That's the specific heat capacity. That little C, specific heat capacity. And I like to think of that as, just like the author, that's why I like him. Thermal inertia. Inertia is a resistance to change. Before it was inertia is resistance to change in motion. This is a resistance to change in temperature. So for water, which has a really high specific heat capacity, a high thermal inertia, a high resistance to change of its temperature, it will take more heat, needs to be transferred to water with a high specific heat in order to have the same change in temperature. As opposed to metal, which metals typically have a low specific heat, less resistance to change, and so their temperature will change more quickly. You don't, for the same amount of heat. Make sense? And then the obvious one. Temperature difference. Temperature difference. If you want to make something hotter, you got to apply more heat. Okay. Thermal expansion. Things when they heat up expand, and we did many things on that. Your reminder was the bimetallic strip. You heat it up. And it bends. Why? Because this has two different metals, as your book explains. They're sandwiched together. And they have different specific heat capacities. So for the same heat that was just transferred, and roughly the same mass on the two sides, different materials. And they change their temperature at different rates for that same amount of heat. The one that heats up faster expands more quickly. Copper. I don't know what they made this one out of. I can't tell. In your book, I think they do, what do they do? Brass and iron? Is that right? Won't hearing mumbling. Anyway, out of that, brass wood. And so it expands more quickly, gets longer, and that makes this thing bend. Let's see. I wanted to do it today on the reverse. Oh, I should do this as a control here. This is liquid nitrogen. I think is this the first time I brought it out? I love this stuff. What's room temperature? About 70 degrees Fahrenheit. What in Celsius? 20. In Kelvin?
Negative 253.
About 393. Yeah, that one's confusing. 0 degrees Celsius, when water freezes, is 273 Kelvin. Absolute 0 Kelvin is negative 273 Celsius. So you get up to 0, 273, and then add 20 more, 293. So room temperature in Kelvin is 293, to give you an idea. This stuff, it's more fun on carpet. Just makes more noise. Anyway, this is 77 Kelvin. That's about negative 196 Celsius, negative 321 Fahrenheit. Cold stuff. You don't want to touch it. So as soon as it hits anything in the room at room temperature, which way does heat flow? Hot to cold. So the internal energy of the ground is transferred into the cold liquid nitrogen. That loses energy. This gains that energy. And they come into equilibrium. But this, it gains so much transfer energy, it boils. Just evaporates on contact. Anyway, that's how cold it is. That's my point. I love this stuff. So let's put it here. Let's do this again. See which way it bends. Okay, to your left. Now I'm going to chill it. Starts cooling and coming back. It's boiling because this is hot. It's starting to bend the other way. Because not only do things expand, they contract. And like you might have guessed, things that expand and get long, they're going to contract too, and you can make it go the other direction. And so you have to worry about that when you're constructing things. You don't want to build it, and then when the temperature starts changing and heat is being transferred and the things expand and contract, that it causes stress in your structural whatever, and crack or break or collapse. That would really stink. Good enough. All right, we did the ring last time. And what happens when you heat up the ring? It expands, yeah. I liked it this way. Let's say you took the ring and you cut it and stretched it out so it was straight. Most people, this would make more sense to. If you heated it up, what would happen? It gets longer. And a little wider, yeah. Okay, do that. Picture it in your mind. And now wrap it back together and make a circle. For some people, that helps see how the hole will get bigger. The thing is still wider and fatter, but the hole is going to be bigger. So that's what it's doing. It's expanding. It does get thicker, but the hole, if you're just looking at the hole seems to get bigger as well. I think that's neat. We didn't heat up the ball, and I couldn't wait for it to cool down, so we'll do it this time. So it fits through now. There we go. Heat up the ball. The ball should have expanded, and you expect it does not get through. So what I tell all the other instructors is, when you get to this point, don't leave it like that. Why? If they left it like that and kept talking the rest of the lecture and then gave it to me, would I be happy? Why? I would not be happy. It transfers heat to the ring, true. True. That's not why I'm unhappy. It'll get stuck and I can't get it out. Yes, when it cools off, it will reduce. If I can cause it to cool off, but just that one. But it stays stuck. It's really annoying. You can get it apart by changing the temperature again, but let's just say it's annoying. Well, I had that happen once. We were moving and had two glass bowls nested in each other. You know what I mean? One was inside the other. And they got stuck. I tried everything. The one I was most proud of was, Windex. Windex has silicone in it. And silicone's can be a good lubricant. And so I was spraying it in there and trying to loosen it. That didn't work. You know what ultimately worked? I tried lots of things. Yeah, well, how did I use hot water? Which one do I put it in? The middle, inside one or the outside one? Yeah, well, I didn't do it. So then what did I try? Cold on the inside. Together it worked. So the cold contracted the inner one and made it smaller, and the heat expanded the outer one and made it bigger, and yeah, I got it free. And how many of you have had a hard time getting a lid off a jar? You know, for multiple reasons. And quite often they'll reduce the pressure inside to preserve the food, and so now you have a pressure difference, and that's making it hard. And then you just put lotion on too, and it really stinks. Well, one way that can work is if you run the jar, can't tip that, here's your lid. You run the lid under some hot water for a while. It should expand a little, correct? But not the jar. And maybe it's easier. I've had that help sometimes.
You can also try to increase the friction by putting a collar.
Yeah, if you you need to get a better grip. First thing I always try, put a towel or a rag or so, because usually it's just because I'm slipping. But even still, sometimes that's not enough. So then I whack on it, try to deform it, and maybe it allows a little leak to get in and equalize the pressure. But sometimes that doesn't work. But sometimes heating it does, and it makes it expand, and that works. Or the combination thereof, or you've loosened it all up and you give it to somebody else, and they go. Yeah, I loosened it for you. But anyway, now how many of you have seen these? They're called fortune fish. You know, they ham it up. They say, fortune teller. If the head moves, you're jealous. If the tail moves, you're indifferent. If they both move, you're in love. If it turns over, you're false. Motionless, you're dead. You know, curls up entirely, you're passionate. So the idea is you set it on your hand and you wait and see if something happens. And that one curls up. Let's see, we got the head and the tail. So let's see, I'm in love. I don't know what they make this out of exactly. It's some type of acetate. But the gist is, it's like a bimetallic strip. Or even if it's not, one side is getting warmed up quicker than the other side. And so there's a difference in expansion, and it bends. It's because of the heat from your hand. So somebody that's cold won't look as good. Or say you put it kind of like some on your fingers and some on here. I expect more heat on the head to happen or something. Yeah, you can see the head starting to move more than the tail. But anyway, those are kind of fun, and you know how they work now. I've always seen them sold as called fortune fish, but anyway. Thermal expansion. Now, at the end of the chapter, it discusses thermal expansion of water. So I want to make sure I go over that. Too high, I'm not that tall. Let's say we got temperature 0 degrees, 100 degrees. This is in your book, in case you don't want to draw it. Volume. All right, water. Let's say we're over here at ice. Ice has a pretty good volume. Do you remember that ice floats? That means it's less dense than water. So for the same amount of H2O in ice form, it takes up more space. Mass per volume, less dense. And so I'm drawing it up here. But when ice warms up, but it's still ice. You can change the temperature of ice. It expands. So it goes up. Well, when it gets to 0 degrees, there's a phase change. And you know, it starts to melt. And as it melts, it drops. And now it's water. And then water heats up. Just like in ice, the molecules are getting more agitated, moving around faster, and they have a greater average translational kinetic energy. And I shouldn't do it this way because this isn't translational, but you know what I mean. And it warms up. And it expands as it heats up. And then it goes to steam, and steam does its thing. Does that make sense? The cool part, I think, with water, it's an exception. Right here, we zoom in on that. If I zoom in right around here, between like 0 and 12 degrees, something special happens with ice and water. Say it starts here at 0. When it starts to melt, it actually contracts. Ice does. And it starts going down. And 4 degrees Celsius water is the most dense. Then from there, it starts expanding again as it heats up. And let's see if any of you already knew or read the chapter. Why is that? Ice has crystals that expand when it's cold. When it's ice. Yeah, it's the crystal structure that forms. If you think of water, this don't go screaming this to your chemistry teacher. I'm just approximating here. You know, so here's some water molecules. They can kind of be randomly jumbled. They can get closer to each other. But when they freeze, they start forming a crystal structure, which is hexagonal. 6 sides. That's why snowflakes have 6 sides. And they are forced to be, maybe if I draw hexagons first, I won't make it look really bad. Not bad. And they end up locking in this structure. Like that. And so you get these open spaces. That's why ice is less dense than water. It's its crystal structure. It takes up more space for the same amount of mass, molecules. Not to scale. So that's why it's less dense. But here we have all ice, that open ring structure. And as they start to melt, those rings, the hexagonal crystal structure, collapse. And they can get closer to each other. And so the density increases. Until 4 degrees Celsius, where we're putting in heat. So not only are we melting and changing the structure, we're giving them more kinetic energy. And they're starting to move around more and more. And what happens when things move around faster and faster? They want to expand. And so those are both happening. But in this region, the collapsing crystal structure is dominating, and the thing gets more dense. Beyond 4, now the thermal agitation's dominating, and it starts to expand. You know, and eventually there's no ice crystals left because they've all melted. Does that make sense? This is very useful, and we're all glad that this is the way it is, because that means ice floats, and the fish like that. Otherwise, the whole pond would be frozen solid. But usually the ice is on the top. And if you read your book, I like how he explains what temperature is the bottom of a really, really cold lake. It's 4 degrees C, because it's the most dense. As the water cools on the surface, eventually some of that surface water becomes 4 degrees, right? And where does it go? It sinks to the bottom. And then the warmer water's on top, and it gets cold. Gets to 4, it sinks. And it's kind of like it fills up with 4 degrees C water. Then what happens if it's all 4 degrees C? The stuff on the top is still, energy is being taken away as it cools off. It gets lower and lower, and eventually it starts to freeze. But it's less dense, so it stays on the top and floats. So all the fish can swim around in the 4 degrees C water and not frozen ice, stuck all winter. So I reserve the right to ask you questions. I can't remember if I put this one on the homework or saved it for the test, or both, wink, wink. Know what happens at 4 degrees C. Because most things expand when you add heat, the temperature increases, and contract vice versa. But water has this little anomaly around 4 degrees. You can cool 4-degree water and it still expands, which is kind of weird compared to most things. Yeah?
It's starting to expand because of what?
It's this play between this and the thermal agitation. So again, from here we're all in ice crystals, bigger structure, less dense. As they start to melt, they collapse and they can get closer together, the molecules. And so the density increases. The volume, because the volume they're just getting smaller. But at the same time, they're starting to get more kinetic energy. Beyond 4 degrees, that dominates, and they start expanding and spreading out.
So if you're moving from 4 towards 0, although you're not at 0 yet, it isn't frozen yet, it's still starting.
They start forming crystals, yeah. Slush, yeah.
Just out of curiosity, are there any substances that you know of that are the same that way, where they expand?
What else? Oh.
Any other than water?
Yes, don't remember. Because they're very rare. And I honestly can't think of one right now. But I remember hearing one. But in our normal everyday chemicals that we run into, no. It's a more exotic one. I'll try to look it up and remember, but yeah, All right. Let's make something expand and move into the next chapter on heat transfer.
Is water the only substance that expands when it starts to freeze?
Is water the only thing that expands when it starts to freeze? And that's where I'm thinking, I'm remembering learning that no, there was something else, but it's not common and I don't remember what it is. This is very rare. And this, if you guys find it before me, that'd be awesome. Yeah, Google's great, but I don't remember. Okay, let's make this piece of plastic expand. It's right here. I've taped it so it's fixed on this end so it can't move. This end's free to move. But I put a little pin underneath and this little, here's my dial, my gauge indicator. High tech. But I think this is cool. This, when it heats up, expands. You think you can notice? No. But it does expand. You hook it up like this. I put a little weight down here. It's just kind of so that it's making good contact with the pen. If this expands, then it's fixed on that end, so it has to go that way, right? Get longer. And if the thing moves that way, it's going to roll over the pen. And the pin's attached to the little indicator. We should see the indicator move if this thing expands or contracts. It's a neat little way of being able to see this effect. Before I lose all my notes. I think that's awesome. You can show this little thing you normally can't see this simply. And that works because as I heat it up, it conducts through. If I heat up these molecules, they start moving around with greater average translational kinetic energy. And they run into their neighbors and give energy to them, and it conducts through it, and the whole thing expands. And if I take some ice and cool it back off, it contracts back, and you can see it starting to turn. Let's speed this up, shall we? And it contracts beyond where we started. So this is a kind of a review of expansion and contraction, but it also is the first method of heat transfer, conduction.
How much longer? It's hard to see it because it's transparent, or at least it looks transparent. How much longer did it get?
Oh, you know, I haven't figured out how much longer it gets, but we could calculate on the order of a millimeter or less, probably. So yeah, very hard to be able to tell just by if you were watching it or even had a little mark. But if you make it roll over that, it's great. This can act as a lever. Remember, it's a simple machine, and we can multiply the force on this needle indicator and make it move a greater distance than this is moving. Moves a little distance, moves a big distance at the cost of force. It's doing the same amount of work because we can't multiply energy, remember? You can't magically create energy, but you can multiply force, and that's what that little lever is allowing us to do and see. I think it's neat. So heat transfer. We have conduction, convection, radiation. All right. Conduction is probably what most are familiar with. All of these are energy transfer. Again, it's a way to transfer. I know I wrote that up there, but I want to emphasize, they're not heat, it's just methods that you can transfer heat. Conduction is by, and these are all defined in your book, by particle to particle. But to help us have a little table to refer to here. It's something when it's in direct contact. Within here I put the ice on the bar, and they're in direct contact, so the molecules can run into each other and transfer energy that way. They're collisions. We did that. Once that gets cold, this spot's cold now. Here's a warmer spot next to each other. So within a material, they're up against each other, and it can conduct through it that way as well. That's conduction, direct contact. Convection is by movement of heated substance. We're used to that as like currents in fluids. Remember fluids? Water, air, gases, liquids. So like a radiator is a classic example. It heats up the air next to it, and hot air is more dense or less dense than the surrounding air? Less dense. So does it sink or float? It floats. It goes up. The buoyant force is less or greater than its weight, so it rises up. Well, what takes its place? The more dense cool air. It heats up, and the convective current flow of the fluid, the movement of this heated substance air, heats us up in the room. Or you can see it in water. You heat up a portion of water, and the same thing happens. It's more buoyant, so it goes up, cold air comes in, and the movement of the heated substance transfers the heat around. Radiation is by electromagnetic waves. Microwaves is an example of an electromagnetic wave. So the rest of the class is me doing demos on this and explaining it further. And answering questions. Conduction. Let's start with these guys. I have 4 different materials: copper, aluminum, brass, steel. Copper, aluminum, brass, steel. Let's take the extremes, copper and steel. I'm going to heat this up. I might as well do it while I'm blabbering. So I'm heating up the middle hub, and it's in contact with each of the bars, and so as heat's transferred to it, it's going to conduct through each bar. But they are different materials, so they have different thermal inertias, and so they will change their temperature at different rates. And that also means it'll conduct through it at different rates, because if one's not as hot, it won't transfer as quickly through the rod by conduction. So heat is being transferred out the rods and hopefully eventually to the wax rings by conduction. This one heats up and he bumps into him, and he heats up and he bumps into him. And they're at different rates, so we'll see who wins. And we can let that go. If you see one drop and I don't hear it, holler. This is a space shuttle tile from the Columbia Space Shuttle. It's made out of the exact same stuff. This is one that didn't go into space, but they had as backup, to go on. It's a piece of the same material. And since they aren't doing that anymore, they made them for sale. So I got one. It's really light. It's mostly silicon and air, but it's cool because I can hold this end and heat it up on the other end. Let's do it this way so you can see. Can you see it glowing? Do it in the dark. That corner is many, many hundreds of degrees Celsius. I don't feel a thing in my fingers. It's still at room temperature. This is a very, very poor conductor of heat. So the hot side over here, heat is not transferred easily through it. It's an insulator. It's a poor conductor. Copper, the first ring. So copper has a higher or lower specific heat capacity? Lower, because it allowed a greater change in temperature more quickly. Good job. And this, does it have a high or low specific heat capacity? Very high. Very high.
The black tiles made something different than the white.
Yeah, they have black and white, and actually no. No. Yeah, interesting. I didn't know that until many years ago, but yeah, they have black and white ones. And that will come up a little more with radiation, the difference between the colors. But
Reflects less light.
black does reflect less light, yes.
So it will absorb more heat.
It does absorb more heat. It also radiates more heat. We'll go discuss that further more. Oh, next one. I stalled long enough. So copper, aluminum. I could probably even turn this off now because it's still hot and it's still going to transfer. So copper, lowest specific heat capacity, then aluminum. It looks like brass is going to go next because I can see it's about through. And then again, this one was steel, to remind you. Now, oh, there it goes. You guys, I was going to do this, but I always forget. You guys have it. You have a wood tabletop and a metal armrest. Put your hand on each one and tell me which one's hotter. You touch them. Which feels hotter? I'm hearing more wood. The metal feels... You're not even doing it. Okay. Okay, most people are getting, the wood feels hotter. Well, we're in the room at room temperature, and for the most part, they're both at the same temperature, especially if you weren't leaning on one. They've come to thermal equilibrium with the air. So they're at 20 degrees Celsius. Why does the metal feel colder? Because we're above, that has to do with it, 20 degrees.
Temperature difference, and metal accepts your heat a lot more easier than wood does.
Well said. There's a temperature difference between you and it. And so which way will energy flow? To it, because you're warmer than they are. And which one's going to take heat away from you more quickly? The metal. And so, well, how does that leave your hand? With less internal energy, so it feels colder. The temperature of your hand will drop more quickly touching metal than wood. And that again has to do with the heat, the specific heat capacity of the materials. And so, yeah, we're used to saying, oh, this one's warmer. Actually, they're the same temperature. But how they transfer heat, and that's through conduction. Better get that guy going. Where are we at? Good. Okay, convection. Convection. Let's do this one, or at least start it. I have a tube of water here. I'm going to light my candle. We got a good breeze going through here. I'll get it closer, I guess, so it won't take as long. And so it's going to heat up the fluid on this side. It should rise. You know what? I want it on this side. That'll get going. These are examples of convection. I love any lecture I can use a lava lamp. So there's a light bulb down here, and it's probably only like 40 watts. Not really powerful. But the blobs of stuff come in contact with it, and it heats up through conduction. But when it heats up, it expands. And what do you think happens to its density? It decreases. So it becomes buoyant, floats up to the top. When it gets to the top, what do you think it does? Cools off, contracts, increases its density, falls back down, heats back up, and it has this little current flow. You get a convective flow through the fluid in here. You can warm it up. That's how a lava lamp works. They use the chemicals, the fluid and the blobs are such so that the density, something's just floating or just sinking. So a little bit of energy transferred to it through conduction can create a good current flow, make it rise and sink. It's a great invention. What are the blobs made out of? They vary. You can make them out of different things, but usually there's some alcohol and funky chemicals I can't remember the name of, sorry. I made a homemade one once. It's never as good as a commercial one, but it did work. You can YouTube it and find out, there's all kinds of recipes out there to make your own. Just be careful, because some chemicals people suggest aren't always healthy. But these are. I mean, I'm not going to eat it. This is a glitter lamp. It doesn't take as much, but hopefully you can see the glitter. It goes up and comes back down. Let's put a drop of food coloring over here now. Now that it's had time to establish a convective current flow, let's see. If I put some red in over on this side, I expect it to sink. Can you guys see it okay? Or is it against my shirt? I wore the wrong shirt today, huh? I don't know if that's helping. So it goes down, that's what I'd expect. But does it just stay put? No. It's driven over. Well, maybe that's just momentum kind of taking it through the corner. The real test will be when it gets over to the other corner. If it stays put, we don't have convective fluid flow. But if that water in that corner is heating up and rising, then we do. I know, exciting, huh? And there it goes. It's starting to go up. I think you can see it well. You can keep watching that. Another fun convection, as you continue to watch that, is this one. Maybe you think that one's not zesty enough. I need the flame. This one, I'm going to use a bigger flame. Oh, it's starting to come around the top corner. And yes, I put it on the right thing this time. Bigger. Huh, that one was less too. It's like our gas pressure is less today or something. Oh, that'll still work. Confetti Theory, hot air is rising. Let's see if we can visualize it. They ride on the air currents that are rising up. Again. So hot air goes up and out. Cold air must be coming in, reheating up, and there's convection going on. That's always good. So he didn't even make it. See, look at that. Steel, higher specific heat capacity. Do I have another convection? Yes, I do. The sun. The surface of the sun sets up little convective cells. So I have some silicone oil in this pan. And I put aluminum flakes in it, little ones, flakes. So when the light hits the wide surface, you can visualize it and see it. And you can see in here that the glitter, comes up in the center of a cell, and you can see it's coming up, and then goes over, and then down around the perimeter of each cell. It's making a little convective airflow. This is a Teflon pan. This is silicone oil. Sometimes you can see this when you're cooking, when it's really hot and maybe you got some spices in there or something with your oil, and sometimes you can start to see it. Even when you're boiling with water, sometimes you can see these little cells come up. The bubbles are rising maybe in one spot and going over. But the surface of the sun actually looks like this too. It sets up these pockets. It's awesome. And they come up in the centers and go down around the perimeters in these little convective cells. And that transfers heat from the core out to the surface. It's one method. It's probably the dominant method on the surface of the sun. How much is this magnified? If I'm looking at these, the average one is about the size of a nickel.
So you can see that with the naked.
And you can, oh yeah, can you see it? You're welcome to come down. Just don't bump it and splash hot silicone oil all over yourself. I'll keep it running after class. But yeah, each one of those is about the diameter of a nickel. That's another of my favorite demos. Radiation. I'm going to turn this guy on.
Why does the heat come up the center and not all air from all areas?
I'll turn this one back off and explain that. This might help. Another little convection chimney. Another candle. And if I put this tube over it, it won't be completely sealed, but mostly. It lights up. This is like your chimney in your house. Hot air is rising. But if the bottom's cold air can't get back in, like over there, then it goes out because it deprives it of oxygen. There's no convective flow, so the heat's not transferred. Or this is not providing enough heat to sustain a convective airflow. However, if you open up your chimney a bit, and the flue on the top, we got that open, but you let some air in, or a different way, slide this down, it stays lit. Because now the hot air can go up one side, and cold air with fresh oxygen can come in the other side. And so it's less energy. It can sustain itself by setting up a convective airflow. It's beneficial it works. It naturally wants to do that. And hopefully that's sufficient to explain that. You pull this back out, and it's trying, but if it's restricted, and the fluid movement, heat trying to move through the fluid, if it can't, because they're blocking each other, you don't get convection. These parabolic dishes, you can't all see it. This has a heat lamp. It's a coil of wire, like your blow dryer or a space heater. And when electricity goes through it, it hits resistance and heats up. And it's going to start glowing, and this half of the room will be able to see it glowing. Well, it's going to transfer heat over to here where I put a match at the focal point. And this works not because this heats up the air next to it, which it does, and that hot air rises, and cold air comes in, and this creates a convective airflow. But that warm air does travel over here. It does transfer some energy to the match, but not near enough. The match needs more energy to light. This match will light because an electromagnetic wave travels through space. It doesn't need air. It doesn't need a fluid to transfer the energy over. It just does it through space. Like the sun heats us up by electromagnetic radiation. These dishes focus it. So that, because electromagnetic radiation, one form of it is light. So think of light, and it focuses it over to here, and then it focuses it onto the match head, and there it goes. The match just lit. Really? I didn't know. Well, that's a dud. A little anticlimactic, okay. I taped a firecracker to the match. 2 reasons. One, it's more fun. And 2, you can't all see the match, so you don't know when it goes, but when it goes boom, you know it worked. And I could tell it didn't go, and that's why I'm, what the heck? But that's radiation. I can't emphasize enough. Convection needs a medium. It needs a fluid. Radiation does not. We'll discuss radiation more, but I want to ask you just one clicker question. Give you guys some credit for being here. One clicker question and you can go. Channel 44, it's open. We discussed this a little last time. I'm confident most of you are going to get this. I sure hope so. But it'll tell me if I need to go over it more next time. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And 72% of you, not all of you, think it's water. You're right. The chapter repeats over and over that water, and has a higher specific heat capacity. The water has less of a temperature change for the same heat transfer. It stays more moderate. The land gets hotter and cooler. Greater change. This is important in climate. Have a nice day.